Welcome back to Math 263. In this video, we will talk about section 11.1. The basic problem we're facing in this section is how to make calculations of function values that are close to values where we know what the function is. So for instance, here we want to look at what is the sine of 0.1, knowing full well that sine of 0 is 0, right? So we want to approximate sine of x for values x that are close to 0 in this case. And as you saw in Cal 1, there's this important idea of this linear approximation, where we say that the function can be approximated by the linear function that gives whose graph is the tangent line at the point. Right? So this is f of x is approximately equal to f of a plus f prime of a times x minus a, and this is the linear approximation at x equals a. So in the case of sine, for instance, if we want to approximate sine of x at x equals 0, we remember that sine of 0 is 0. The derivative of sine is going to be cosine. So that means that if I want to calculate f prime of 0, that means we're calculating cosine of 0, which is 1. So that gives me that sine of x is approximately equal to 0 plus 1 times, well, x minus 0. So that means that sine of x is approximately equal to x itself. And that's an example of using a linear approximation to a function. Okay, in green here, we see the line that's tangent to our curve y equals sine x, right? So this, in black, we have the curve y equals sine x. And in green here, this is the line y equals x, which is the tangent line to my curve at the origin, but it's also the linear approximation, the graph of the linear approximation that we calculated. And that's just the meaning of the linear approximation. It's the function whose graph is the tangent line. So that was what we found as the linear approximation for sine x. And if you look at our picture, right, it's very convincing that y equals x gives a very good approximation as long as x is not too big. Right, so sine x is approximately equal to x for x small. So that's the first thing we found. Now let's look at this orange line here. So this is the tangent line at x, which is going to be 3 pi by 4. And we'd like to calculate what sine of x is at 3 pi by 4 and what cosine of x is at 3 pi by 4. So for that, we're going to make an appeal to our trig circle. So let's draw ourselves a little trig circle. Pi by 4 is that angle right there. Here we have pi over 2, and here we have 3 pi by 4. Now if we look at our diagram, this pi over 4 is one of the angles that we know the cosine and sine for. So at pi over 4, cosine and sine are equal to each other, and we get cosine of pi over 4 is root 2 over 2, and sine of pi over 4 is root 2 over 2. Now, the next thing we have is that by looking at the symmetry of this picture, we see that sine of 3 pi by 4 is exactly the same thing as sine of pi by 4. So we're going to get root 2 over 2 here. And then cosine is going to be the opposite. So that's going to be negative root 2 over 2. Okay, so now using our linear approximation, right, we just need to calculate sine at 3 pi by 4. And then we're going to calculate the derivative of sine, which is cosine, again at 3 pi by 4. And then we get x minus 3 pi by 4. And so this is the formula for the linear approximation. And this gives us root 2 over 2 minus root 2 over 2 times x minus 3 pi over 4. And this is a good approximation to sine x for x near 3 pi over 4. So that's the difference between these two linear approximations. The green one is going to be a valid approximation near 0, and the orange one is going to be a valid approximation near 3 pi over 4. Okay, in general, we're going to have this idea now of a Taylor polynomial of order n. So the nth order Taylor polynomial is going to be a polynomial of degree n. So the degree is the power of x that appears in it. And we're going to say it's centered at x equals a. And this is going to be then given by a formula where we take f of a plus f prime of a times x minus a. Then we're going to take the second derivative of a at that point divided by 2 factorial multiplied by x minus a squared. And then we keep going with powers of x minus a divided by the appropriate factorial, and then we're going to take the appropriate number of derivatives of this f. So the highest order term is going to be the nth derivative of f evaluated at a divided by n factorial times x minus a to the x minus a quantity to the power n. Now I'm going to point out that that notation there, this f n of x, means the nth derivative of this function f, where I use the round brackets like that in this. So that's not an exponent, that's a number of derivatives. Okay, and this is going to be the best approximation to my function f among all the polynomials of degree n. And just a little linguistic point here, if we take the polynomial that's centered at x equals 0, this is sometimes called the Maclaurin polynomial, instead of saying it's the Taylor polynomial centered at 0. That's just a language point. This is a fundamental formula that you need to know, and you know it already in the case of n equals 1. Right? In the case of n equals 1, this is the linear approximation. And there's a special name for it in the case n equals 2. N equals 2 is called the quadratic approximation. In practice, those two are going to be the most important ones in most applications, though high-order Taylor polynomials do find use in many applications. But I would say that easily 3/4 of the applications of Taylor polynomials are actually using linear approximation, and then another good chunk of them are using the quadratic approximation. Okay, so let's do an example calculation. Let's find the p0, p1, and p2 for root x centered at x equals 9. Okay, so p0 is kind of a silly thing to calculate, because that's just going to be the value of the function at x equals 9. But it fits into our formula, right? We have that p0 is then just going to be the function at 9. So that's going to be root 9. So that's just 3. Okay, so for p1 we need to calculate not just root 9, but we need to calculate the derivative. So let's calculate that. And so f prime of x, if f of x is root x, f prime of x is 1 over 2 times the square root of x. So f prime of 9 is going to be 1 over 2 times the square root of 9. So that's 1 over 6. So that means that p1, we're going to get f of 9 plus f prime of 9 times x minus 9. So that's going to be 3 plus 1 over 6 times x minus 9. Okay. Let's now calculate p2. Well, p2 involves taking some second derivatives. So let's calculate the second derivative. We already have the first derivative we've calculated. So the second derivative we're going to take, right, so we're going to get 1/2 times x to the negative half, right, I just rewrote the derivative, and we're going to take a derivative of that. We're going to get 1/2, and then we're going to multiply by -1/2, and we're going to get x to the -3/2. So that's going to be -1/4 x to the -3/2. And we're going to want to evaluate that at 9. So that's the next calculation we need to make. So that gives us f double prime evaluated at 9 is going to give us, here we get -1/4 times 9 to the -3/2. So that's -1/4, well, the square root of 9 is 3. So that's 9 to the half power. So 3 to the 3 is 27. So this gives us -1/4 times 27, which is -1/108. So now our P2 of x is going to be, we can take the P1 part, that's going to be 3 plus 1/6 times x minus 9, and then we get -1/108 times x minus 9 squared, whole thing over 2. So this is now, well, we can simplify this up a little bit. But this now gives us the quadratic approximation to root x centered at x equals 9. Okay, let's do another example. Let's find the nth Taylor polynomial for the exponential function e to the x, where we're going to center it at x equals 0. Now this is a nice problem because we know how to find all the derivatives of e to the x. Right? So we have that if f of x is e to the x, then f prime of x is e to the x. F double prime of x is also e to the x. F triple prime of x is e to the x, and so on and so forth. And the nth derivative is also going to be e to the x. Super simple example. Good. So now at 0, right, we have f of 0 is 1. F prime of 0, well, that's just e to the 0, that's 1. F double prime of 0 is 1, so on and so forth. And all these derivatives at 0 are going to be equal to 1. So this means that Pn of x is going to be 1 plus, we're going to get just x, then we're going to get 1/2 factorial times x squared, and then we're going to get 1/3 factorial times x cubed, plus 1/4 factorial times x to the 4th, so on and so forth, all the way up to 1/n factorial times x to the n. And this is now the nth order Taylor polynomial for e to the x. Centered at 0, right? Centered at 0. And so here's a little visualization to help see what's going on. Right, so here in black we have e to the x. Then in green we have the linear approximation, right? That's y equals 1 plus x. The orange curve is the quadratic approximation, right? You can see it's sort of filling out a parabola. That's going to be y equals 1 plus x squared over 2. And then this blue curve down here, that guy is going to be the degree 3 approximation, the cubic approximation, if you will. So that's going to be x cubed over 3 factorial, which is 6. And so that's 6 is equal to 3 factorial. So that's what this blue curve is. And as you see, when x is very close to 0, these curves, as I increase the degree or the order of the Taylor polynomial, it's getting better and better. It's getting to be a better and better approximation. But then when we move far away from 0, these approximations are actually quite bad. So that's something that's important to remember. These approximations are very local to the center of the Taylor polynomial. Okay, so let's do an example now where we compute some Taylor polynomials for sine of x. So here we're going to take it at x equals 0. But before we do that, let's just go ahead and calculate a whole mess of derivatives. Right, so I have, if f of x equals sine x, then f prime of x is going to be equal to cosine x. F double prime of x is going to be negative sine x. F triple prime of x is going to be, the derivative of that is going to be minus cosine x. And now if I take the quadruple prime of this, so f superscript 4 here in round brackets, that's going to give me sine x. The fifth order derivative, I'm going to take the derivative of sine x, I'm going to get cosine x again. And you start to see this pattern, right? These derivatives are going to repeat every 4 derivatives. So the function itself is going to be sine of x, and the fourth derivative is going to be sine again. The first derivative is cosine, the fifth derivative is also cosine, and so on and so forth. So we're going to see this kind of a pattern here in the coefficients of the Taylor polynomial. So here we're going to get that P0 is 0. P1 is going to be x. Right, we saw that already. P2, we're going to get x, and then we're going to get plus the second derivative evaluated at 0, so that's going to be x again. There's no quadratic term. Right? That's because we're going to notice that the even derivatives that we take here are 0 at 0. So P2 is x again. Then P3, we're going to get x, and then we're going to take minus, here we're going to get cosine at 0, which is 1, so minus 1 over 3 factorial times x cubed. Okay, p to the fourth, we're going to now evaluate sine of x at 0, which is 0, so we get the same thing again. And then p5 is going to be what we get by evaluating cosine of x at 0, which gives us 1. So we're going to get x minus 1 over 3 factorial x cubed plus 1 over 5 factorial times x to the fifth. P6 is going to be the same thing again. And it's not, I'm not going to recopy it, but P6 we're just going to pick up a sine of x evaluated at 0. And we're going to repeat this pattern. Right? So in general, if I want to go, let's say Pn when n is odd, we're going to get this thing that looks like x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the 7 plus and minus and plus and minus, and then at the end we're going to get, depending on, we're going to look at the parity of this, and we will get something that looks like 1 over n factorial x to the n here when this n is odd, right? And we just alternate these signs. So this is going to give us the Taylor polynomial for sine of x for general n. Okay, so here is a little visualization of it. In black here I have y equals sine x. My green line is P1, which is also the same thing as P2, right? So that's both the first order approximation and the second order approximation to my function. And then the third order approximation is going to be this orange one, and that's going to be P3, that's also P4. And then finally this blue one, that's looking really, really stunningly close to my function, that's going to be P5, which is the same thing as P6. Okay, and I purposefully truncated my graph here, because if I were to go out further, if you look at the formulas we have for all of these, right, all of these are polynomials. So their limits as x go to plus and minus infinity are going to be plus or minus infinity. So these things are going to behave very differently from sine of x for large values of x. And so that's another reminder of the fact that the Taylor polynomial is useful for approximating our function near a point. It is not a global approximation to the function. Let's try to get a handle on the error terms and to what extent our approximation is a good approximation or a bad approximation of our function. So that's what we're going to look at now. But before we do that, let's make a little side detour into a topic that hopefully you remember from Cal 1, but if you don't, I'll just draw you a sketch and hopefully it'll be clear. So what we have here is the mean value theorem. So let's think about, I'm going to pretend that the mean value theorem is talking to us about the 0th order Taylor approximation. Right, so let's think about what the mean value theorem says. The mean value theorem says if I have, let's say I have a point, I don't know, I have some function here. I have a point, let's call this point A and this point X. Then what it's saying is that if I look at the average slope between those 2 points, there's going to be some point here on my curve where the tangent line is parallel to that secant line. Right, so here on the left, I have the slope. Let me draw that. Right, that guy is the slope of that line. And the guy on the right, right, if that's my tangent line, then this is going to be the point C. So what it's saying is that if I have a point A and a point X, then I look at the line segment connecting the 2 corresponding points on the graph of my function that has some slope. There is some point in between them where that's the slope of the tangent line. Right? So that's what the mean value theorem says. And now after doing some algebra, right, I'm going to move that denominator x minus a over to the right-hand side and then move f of a over. I end up with this formula over here, which says that f of x is equal to f of a plus f prime of c times x minus a. Now, why did I do this? Well, I want to think of this not as being f of a, but I want to think of that as being the 0th approximation, or the 0th Taylor polynomial for f. Okay, so having made that interpretation, hopefully what I'm about to say seems natural or plausible, which is that In general, if I look at f of x minus its nth order Taylor polynomial, I'm going to have a term that looks like the n plus first derivative of my function evaluated at some point between x and a, and then I get this kind of x minus a to the power n plus 1 divided by n plus 1 factorial. Right, so that looks like the mean value theorem, but kind of taken up a level to higher derivatives. Okay, so for this to be a true statement, I need some hypotheses. We need that f has n plus 1 derivatives, and the n plus first derivative should be continuous. And then this gives us what's called the error term, or the remainder term from Taylor's theorem. So this theorem is called Taylor's theorem, and this expression is called the Lagrange form of the remainder. We're just going to call this Taylor's theorem, and that's all we're going to use. We're not going to see any other forms of the remainder, but I'm just telling you this language so you can, when you see it in the Khan Academy or one of the other videos that I've linked, you will see that right, they refer to it this way. So I'm giving you the language so you can connect with other things. Okay, so let's go ahead and use this in order to deal with a problem. So here we're going to ask the question, what is a bound on the error if we approximate cosine of 0.1 using the fourth order Taylor polynomial centered at x equals 0? Okay, so here we need to think for a second. Right, so what is the fourth order Taylor polynomial centered at x equals 0? So here we're going to remember we have cosine of x. Let's say that's f of x. Then f prime of x, we're going to get negative sine of x. F double prime of x is going to be negative cosine x. And f triple prime of x is going to be sine of x. And that means then that the fourth derivative is going to be cosine of x. Right, so this is looking awfully familiar from our sine example. Right, and this list is going to repeat itself repeatedly with period 4. So this means we get that P0 is going to be 1. Then that's also going to be P1. Then P2, we're going to get 1. We're going to get minus cosine of 0, which is 1, times x squared over 2 factorial, which is just x squared over 2. And then P3 is going to be the same thing. Right? This is a behavior very similar to what sine was doing. Then P4 is the one we're interested in. We're going to get 1 minus x squared over 2, and then we're going to get plus cosine of 0, which is 1, over 4 factorial times x to the 4th. Okay, we could stop there, but this question, I think, it's more interesting if we think of this a little bit as a little bit of a more sneaky thing, right? We know that this is also the fifth order Taylor polynomial. So now we can say, using the error term, we can say that cosine of 0.1 minus P5 at 0.1, well, that's going to be equal to, now I'm going to use Taylor's theorem with its remainder term, we're going to get the sixth derivative evaluated at some point c. We're going to divide this by 6 factorial, and we're going to multiply by the x value, which is 0.1 here, to the power 6. Right, that's applying the error term that we had on the previous page. Right? That's the error term, or the remainder term. And the nice thing about this, right, the sixth derivative of cosine, and so we have, the sixth derivative here of cosine is just going to be negative cosine x, right? Looking at our pattern, we get that the second derivative is negative cosine x, and then it repeats every 4. So that's negative cosine x. And here we're thinking of c, right, and we have c is going to be between 0 and 0.1. So negative cosine is going to be, this is going to be something that's negative, right? That's going to be a negative quantity because cosine is positive for c between 0 and 0.1. And it's going to be no more negative than minus 1. Right? So that's going to be, on the one hand, this quantity is going to be, right, so that tells us that this error, the remainder, is negative. But on the other hand, the remainder is also, I'm just naming that thing remainder, that is going to be greater than or equal to 1 over 6 factorial times, negative 1 over 6 factorial times 0.1 to the power 6. Right, so that gives us a great deal of control on the amount of error we have. This is a tiny number. That's like 10 to the minus 6 divided by, that's like a ballpark of 700-ish. Maybe 720, I want to say. So that's a really, really tiny number that we have here. And obviously this remainder, we're saying it's negative. So that means that P5 is an overestimate of our value there. Actually, I should mention that this analysis of these Taylor polynomials is actually incredibly useful in application, because one large family of functions that one can encounter and have to deal with are things where the function itself is maybe not known. You don't have a formula for it. Instead, it comes as the result of either experimental measurements or as the result of running a simulation. Both of those things, you might be able to extract information on maybe a derivative, or if you really have a great simulation, maybe 3-4 derivatives, even though you don't have a formula for the function. So this then allows you to make simulations, get some grid points where you estimate your function and then interpolate between them. Okay, so this is useful in a number of different areas. One simplistic area where it's useful is something like a video game. Right? If you have a video game with some kind of physics going on in your video game, maybe you don't need it to be super duper accurate. You just want it accurate enough but fast, so you can have a real-time experience of the game. In that case, maybe you make some approximations. If you have some things involving taking square roots, you take one of these linear approximations or perhaps a quadratic approximation, because that's a faster calculation than doing some of the numerics. That's one example. Another example, a friend of mine in graduate school, before he went back to graduate school, and he had worked trading currency, if I remember correctly. And he was saying that, so this was before everything got automated, so now it's all, to the best of my knowledge, it's all done by computer. Back then it was done by actual people who were trading and buying and selling currency from each other, representing different banks. And he was saying that what they did was they started out the day with like a phone book's worth of data that had been developed by the overnight simulation that had been run on some fancy computer. And the simulation gave you these tables that had function values and their derivatives, not just first derivatives, but maybe second, third, fourth derivatives. And these people trading currency went and interpolated values between what was in their table from the simulation. They interpolated it using Taylor's theorem. And he was saying that the thing that just blew him away was some of the old currency traders who'd been there a long time could calculate these fifth-order Taylor polynomials in their heads really, really fast. And they used that to be able to buy and sell currency and make money, basically, by being really good at Taylor's theorem. So those are two sort of example applications that are a little bit surprising, but applications of Taylor's theorem show up everywhere in the applications of mathematics, in engineering and physics, in all of these areas. If you have a problem you can't solve, sort of the first idea to do is to maybe expand it as a Taylor polynomial and see if you can use that to understand what's going on.